Hello and welcome to this last module on treatment technologies. After reviewing the technologies treating wastewater and effluent, we will now tackle a very important but often neglected topic: sludge. Sludge in all its forms and all its names: fecal sludge, septage, secondary sludge. One product: sludge. Sludge is a very variable product. It can be fresh, old, stabilized, unstabilized, thick, diluted, yellow, black. What is sure is that it is much more concentrated than wastewater. Let's consider, for example, fecal sludge, meaning the sludge coming from on-site sanitation technologies such as pits or septic tanks. The factors which influence the characteristics of fecal sludge are the tank emptying technology and the patterns of emptying, the performance of septic tanks, the intrusion of groundwater, temperature, admixtures to fecal sludge like grease, kitchen or solid waste, and of course, the storage duration, which can last from months to years. These characteristics have practical implications for treatment. For example, sludge which is still rich in organic matter and has not undergone significant degradation is difficult to dewater. Conversely, sludge that has undergone significant anaerobic degradation, such as from septic tanks or ABRs, in other words, which is stabilized, is more easily dewatered. All these factors influence fecal sludge characteristics. Fecal sludge is a very variable material. Consequently, management systems need to be designed on a case-by-case basis. The four main functions of sludge treatment are the solid-liquid separation, stabilization, dewatering or drying, and pathogen reduction. It is important to define the end-use or disposal option and select the appropriate treatment level accordingly. Sludge will not be treated the same if it is to be used for agriculture or in a cement factory. Potential beneficial end uses are dry sludge as a fertilizer, dry sludge as a fuel, or biogas, for example. The different treatment technologies can be categorized according to the four functions which I just mentioned: solid-liquid separation, stabilization, dewatering or drying, and pathogen reduction. The technologies in dark yellow are those which are commonly applied for fecal sludge treatment in low and middle-income countries and which are presented throughout this course, some of which already in Module 3.2. The technologies in pale yellow, on the other hand, are mainly applied in Western countries, such as the filter press, or under investigation in low and middle-income countries, such as the sludge pelletizer. Please note that some technologies may fulfill two functions, such as the IMOF tank or the planted drying bed. Let's start with the sedimentation thickening ponds, whose function is solid-liquid separation. Such ponds allow the sludge to thicken. As the sludge settles and digests, the supernatant must be decanted and treated separately. The thickened sludge can then be dried or further composted. Two tanks operated in parallel are required so that one can be operated while the other is emptied. To achieve maximum efficiency, loading and resting periods should not exceed 4 to 5 weeks. The main drawback is that the thickened sludge needs to be removed by a front-end loader. This technology is relatively low cost, but requires a large land area, if possible far from habitations, as it generates odors and flies. Let's now move to the most common sludge treatment technology, the unplanted drying bed. The bottom of a drying bed is lined with perforated pipes to drain the leachate away. On top of the pipes are layers of gravel and sand to support the sludge. The bottom layer should be coarse gravel and the top one fine sand. Thus, the liquid part of the sludge can both infiltrate and evaporate. The sludge, however, is not effectively stabilized and its pathogen content is still high. According to the end use, for example as a fertilizer, it must be further stored or treated. Dried sludge can be removed after 10 to 15 days, according to the climate conditions. After the unplanted drying beds, let's move to the planted drying beds, which is much better at pathogen reduction. The key improvement of the planted over the unplanted drying beds is that they don't need to be dislodged after each feeding and drying cycle. The plants and their root systems maintain the porosity of the filter, which means that sludge can be added layers after layers, which imply also a much longer retention time. Thus, this technology leads to a much better stabilization of the sludge, which is partly converted into humus. The appearance of the bed is similar to a vertical flow constructed wetland, as we saw in the last module. The filtrate flows down through the filter and is collected through a drainage system. Ventilation pipes connected to the drainage system contribute to aerobic conditions in the filter. When constructing the bed, a free space of about 1 meter should be left above the top of the sand layer to account for about 3 to 5 years sludge accumulation. Sludge should be applied in layers between 75 and 100 millimeters thick and reapplied 3 to 7 days. Obviously, plants are crucial in planted drying beds. The startup and acclimatization phases are very important and requires much care. Finally, let's have a look at co-composting. Co-composting is like compost, but using more than one feedstock. In this case, sludge is added to organic solid waste. Composting is the aerobic degradation of organics. It can be done in two ways, either open or in vessel. In open composting, such as shown in this figure, the mixed material is piled into long heaps called windrows and left to decompose. The piles are periodically turned to provide oxygen and ensure a homogeneous treatment. For dewatered sludge, a ratio of 1:2 to 1:3 of sludge to solid waste should be used. Compost sounds simple, but the mixture must be carefully designed so that it has the proper carbon-nitrogen ratio, moisture, and oxygen content. Co-composting is quite labor-intensive, so it only makes sense if there is a demand for the product from customers that are willing to pay. To sum up, we saw that sludge is a highly concentrated and variable material. Before constructing a fecal sludge treatment plant, it is necessary to make a good assessment of the initial situation in the city and estimate the characteristics and quantities of the sludge to treat. This can strongly influence the choice of technologies. For example, fresh sludge from public toilets needs to be digested and stabilized, with the possibility to produce biogas. On the other hand, sludge from septic tanks is already digested and usually ready for dewatering or drying. Fecal sludge management requires an integrated planning approach. It is more complex than conventional systems, where a sewer network brings the wastewater to the treatment plant. In fecal sludge management, there are many more stakeholders to bring on board, starting with the manual and mechanical service providers, as discussed in Module 2.8. For fecal sludge to reach the treatment plant, there are often new management and financial schemes to be put in place, agreements to be reached, and sometimes even new policies to draft. Think about it. To learn more about the different sludge treatment technologies and about fecal sludge management planning, we recommend you to refer to Eavac Sandek FSM book, which you can download for free at the link below. Finally, do not forget that the sanitation system does not end at the treatment plant. A treatment plant also generates products which need to be disposed of or, in the best case, reused. How to dispose and how to use, that's what you will discover in the next series of modules with Lukas Ulrich. Enjoy!